Here are some interesting facts about oxygen and hydrogen. Oxygen is the most abundant chemical element. It is nearly a fifth of the volume of the great ocean of air called the atmosphere, and at the bottom of which we live. In every 100 pounds of the waters of the earth, there are 90 pounds of oxygen. There is much oxygen in the minerals in the earth's crust as all other elements combined. Dig anywhere in the earth and you encounter compounds of oxygen. It is in plant and animal substances and hundreds of rocks and minerals. Oxygen has no color, taste, odor, but under ordinary conditions it is an invisible gas, but when cooled to an extremely low temperature and under heavy pressure, it is a blue liquid. If the pressure is further increased, liquid oxygen becomes solid. There is no other element so important to men and animals. They must breathe it every minute of the day and night in order to live. When a substance burns, it combines with oxygen. Oxygen is necessary to burn fuels for cooking, warmth, and generating power to operate machinery. It combines with nearly all other elements to form compounds called oxides, O-X-I-D-E-S. Like oxygen, hydrogen has no taste, color, or odor. It has the distinction of being the lightest member of the whole family of elements. Because it is lighter than air, it rises in the atmosphere and is so used to fill the envelopes of airships and balloons. In America, where there is a supply of helium, this gas is used in balloons and airships in place of hydrogen. Helium is lighter than air, but is not as light as hydrogen. It has the advantage that it does not burn or explode. Hydrogen burns readily, and in burning gives out considerable heat. When mixed with the right amount of air and ignited, hydrogen burns so quickly that it explodes. When hydrogen is burned in oxygen in a hydrogen torch, the flame creates such a high temperatures that it is used for welding and cutting metals. Most of the gaseous and liquid fuels used for power and heat contain hydrogen. Nearly one-half of the volume of the gas used in stoves is hydrogen. It is hydrogen burning in the sun that provides the heat and light essential to life on our earth. All of the chemical compounds known as acids contain hydrogen. In fact, it is hydrogen which gives to them the qualities which make them acids. Animal and vegetable substances such as fat, butter, sugar, and meat contain hydrogen in combination with carbon and oxygen and other elements. Hydrogen has widespread use for converting coconut oil into margarine and cheap substances like fish oil and low-grade coal into valuable substances. Hydrogen is used to solidify cottonseed and coconut oils so that they can be used as substitutes for lard and butter. It is also used in making synthetic rubber. Hydrogen is indeed a useful member of the family of elements. When the test tube in which hydrogen is collecting is nearly filled with the gas, carefully withdraw the carbon rod and slip your thumb over the open end. You must do this while the end of the tube is below the surface of the electrolyte in the bowl, so that no hydrogen escapes and no air enters. Light a match, lift the test tube out, and turn it right side up. Remove your thumb and quickly, before the hydrogen escapes from the tube, apply the match flame to the open end. If you do this quickly, there will be a flash of blue flame and a sound like plop as the hydrogen burns. There is such a small quantity of hydrogen in a 6-inch test tube that it can be ignited without danger. However, if you attempt to burn hydrogen contained in a bottle or jar, the larger quantity would explode with enough force to shatter the glass and probably injure you. The fact that the gas collected in the test tube burned is proof enough that it is hydrogen. The gas which collects from the carbon rod connects. The positive terminal of the battery contains a very small amount of water vapor. However, the amount of water vapor is so small that we can consider it to be pure oxygen. Alone and unaided, oxygen does not combine with many substances at ordinary temperatures. When it does, its action is slow, for example, as in the rusting of iron. If heated, the action of oxygen is very rapid, often resulting in terrifying explosions and fires. It is fortunate that 4/5 of our atmosphere is nitrogen, because nitrogen dilutes the oxygen and slows it down. If the atmosphere were pure oxygen and a spark or a flash of lightning occurred, everything on the surface of the earth would burn up. When the test tube containing the oxygen is approximately half filled, remove the carbon rod and put your thumb over the end of the tube. Do not let any of the solution escape from the tube, or air will enter and dilute the oxygen. Turn the tube right side up and keep it closed with your thumb. Light the end of a broom straw, and when it is blazing, blow the flame out. The end will glow for 2 or 3 seconds. While it is still glowing, but there is no flame, remove your thumb from the tube and thrust the glowing end into the oxygen. It will immediately burst into flame. The tiny spark heated the oxygen enough to speed up its action and cause a broom straw to burn with a flame. Hot metals, even a hot diamond, thrust into pure oxygen are quickly burned up. When a diamond is burned in oxygen, carbon dioxide is produced. If the carbon dioxide is dissolved in water, the result is club soda. However, that would be a costly way of making this beverage. Hard and soft waters. Water which passes over the surface of the earth or soaks into the earth may dissolve some of the minerals which it meets. It often picks up calcium, magnesium, and sodium compounds. The water used for drinking, cooking, and washing contains a very small trace of sodium in the form of sodium chloride, which is, as you know, common salt. Such water is called fresh water to distinguish it from seawater and the water from brine wells, both of which contain a large quantity of salt and other substances. Fresh water, which contains very little or no calcium or magnesium, is called soft water. It is desirable that drinking water contains small quantities of these minerals, which are required to carry on the chemical processes which take place in the bodies of men and animals. Too much mineral makes water unfit to drink. When more than 100 pounds of calcium, magnesium, or iron are present in 1 million pounds of water, these minerals are objectionable and a nuisance. Such water is called hard water. There are two kinds of hard water, temporary hard water and permanent hard water. Temporary hard water contains either calcium bicarbonate or magnesium bicarbonate, which it has picked up from the earth and can be easily softened by boiling. Boiling converts the soluble bicarbonates into insoluble carbonates. Large quantities of temporary hard water can be softened by adding a carefully adjusted amount of calcium hydroxide to the tank or reservoir in which they are stored. The calcium hydroxide changes the soluble bicarbonates into insoluble carbonates, which settle to the bottom in the form of a white precipitate. Permanent hard water usually contains sulfur or calcium sulfate or calcium chloride. It may also contain magnesium sulfate, magnesium chloride, iron sulfate, or iron chloride. Boiling will not soften permanent hard water. It can be softened by adding certain chemical substances. A common softener for hard water called permute is a sodium silicon aluminum compound. Hard waters occur in many localities and are a problem in laundering and in household and manufacturing processes. It is difficult to clean with hard water, for it does not form a good lather with ordinary soap. To make suds with hard water, a hard water soap made especially for hard water must be used. Hard water is also objectionable because it forms a mineral deposit called scale on the inside of pots, steam boilers, tanks, and pipes. Those who live in a hard water area will not be interested in this experiment. They are quite familiar with the sad results obtained when ordinary soap is used with hard water. We can make some soapy water by dissolving a few shavings cut from a cake of ordinary soap, not hard water soap, in a tumbler full of soft water. Rainwater and distilled water, which is used for storage batteries, are excellent for this experiment. Pour half of the soap solution into another tumbler and set both tumblers on the windowsill where daylight will shine through the soapy water. This will enable you to see what happens when you mix hard water with the soapy water. The hard water is prepared by adding 1 teaspoonful of plaster of Paris to a quart of soft water. Do the mixing in a clean fruit jar. Plaster of Paris, it has been explained, is calcium sulfate, which has been heated so as to drive out its water crystallization. It is only slightly soluble, and it is best to prepare the hard water used in this experiment several hours in advance. Let it stand overnight, and the calcium sulfate, which does not dissolve, will sink to the bottom of the fruit jar. Pour some of the clear hard water from the fruit jar into one of the tumblers containing the soapy water. The second tumbler of soapy water is not disturbed, but serves as a control with which to compare the soapy water to which the hard water was added. The hard water will cause the soap, which was dissolved in the soft water, to leave its solution and form sticky white flakes of a calcium soap which is insoluble. The chemical name for ordinary household soap is sodium stearate. The chemical name for the sticky, insoluble calcium soap which ordinary soap becomes in hard water is calcium stearate. It is this insoluble calcium compound formed when hard water mixes with soap that causes the ring around the bathtub, a scum on dishes, and a gray film on linens. We can soften permanent hard water. Water which, in passing through the ground, comes into contact with gypsum, dissolves some of the mineral and becomes permanent hard water. The calcium sulfate, which it then holds in solution and is the cause of its hardness, can be removed with washing soda. When washing soda is added to the water, calcium carbonate and sodium sulfate are formed. Calcium carbonate is insoluble and settles to the bottom in the form of fine white powder. The sodium sulfate remains dissolved in the water, but is not particularly harmful to metal or cloth and does not interfere with the cleansing action of soap. If magnesium sulfate is also present in hard water, lime must be used in addition to the washing soda. You can demonstrate the action of washing soda in softening water. If you have on hand some of the hard water containing calcium sulfate, which you prepared, you can use it in this demonstration. Otherwise, add a teaspoonful of dry powdered plaster of Paris to a quart of water contained in a fruit jar. Stir well and let stand overnight. Pour some of the clear hard water into a tumbler. Dissolve a teaspoonful of washing soda in half a tumbler full of water and add some of this solution to the hard water in the first tumbler. A white, cloudy precipitate of calcium carbonate or powdered chalk will form immediately. If the tumbler is left undisturbed, the chalk will settle to the bottom. The water in the tumbler has been softened. If you doubt this, use it together with some ordinary soap to wash your hands. It will make a good lather. Our next part will be on combustion, the chemistry of a flame, oxygen, which supports combustion, and where does a burning candle go, wood, charcoal, destructive distillation, and the treasure in a pile of coal. Chemistry makes all things interesting. Consider such a commonplace object as a burning candle. It may be on a birthday cake or shedding its soft light in the church. There is a great deal of chemistry involved in a candle and its flame. They bring to our attention the immediate or important chemical action called combustion, and can be used for several experiments. What is a flame, and what does burning mean? A flame of any sort is burning gas, and burning is combustion. The simplest way to explain combustion is to state that any chemical action producing heat and light is combustion. Combustion is utilized to cook food, melt substances, weld metals, bring about chemical actions, heat and light, our buildings, propel automobiles, trains, ships, and airplanes, and to drive the machines of industry. Without combustion, we would have to eat raw food and use muscles to do the work which motors and engines now perform. It would be difficult to keep comfortably warm in winter except in a tropical climate or in a tunnel deep underground. In a cold climate, the temperature is much warmer in a mine during winter than it is above ground. Of course, electrical generators driven by water power furnish a limited amount of heat, power, and light. Combustion does not supply it all, but water-driven generators could not possibly fill all of our needs. It is necessary to burn a vast amount of coal, oil, wood, and gas to supplement our hydroelectric power. The most common type of combustion is the union of a substance with oxygen. Any material burned for the purpose of producing heat, light, or power is called a fuel, F-U-E-L. Coal, wood, natural gas, peat, and oils are our principal fuels. They consist mainly of carbon. The waxes in a candle contain a great deal of carbon. They belong to the group of compounds called hydrocarbons. Petroleum and gasoline are the two most well-known hydrocarbons. Any sort of fire, whether it is a candle flame, a blazing building, or the glowing coal, oil, or gas in a stove or furnace, results from the rapid union of some substance with oxygen. Without the oxygen, there would be no fire. The oxygen for fires is usually supplied by the atmosphere. Fires require oxygen. One of the best ways of putting out fires is to deprive them of oxygen. The fire extinguishers, which spray carbon dioxide, fomite, or carbon tetrachloride, or on a blaze, shut off the oxygen and literally smother the fire. Shutting off the oxygen supply from a burning candle will extinguish its flame. We can use a few drops of melted candle wax to fasten a birthday cake candle or a candle stump about 2 inches long in an upright position in the center of a cake pan or a pan. Fill the plate with water and light the candle. Set the 1 pint glass mayonnaise or fruit jar over the candle and let it rest on the bottom of the plate. In a moment, the candle flame will flicker and go out. The flame has been smothered because it has burned all of the oxygen out of the air inside the jar. No more air can enter the jar because the open end is below the surface of the water. The water in the plate will rise inside the jar and fill the space which the oxygen formerly occupied. The air space remaining in the jar contains principally nitrogen. There is some carbon dioxide also present, but this soon dissolves in the water. Why fanning or blowing a fire makes it hotter? A bonfire always burns more furiously when the wind is blowing. There is no mystery about this. The reason is that increasing the supply of oxygen makes a fire hotter. Wind supplies a bonfire with more air that would would ordinarily reach it on a windless day. You may have seen how an increase in the supply of oxygen will make a glowing ember burst into flame. You can also perform this experiment with oxygen obtained from hydrogen peroxide. Pure hydrogen peroxide is a clear, syrupy liquid about half again as heavy as water. It is something that only a chemist sees. Concentrated hydrogen peroxide is used to drive torpedoes and submarines. The ordinary variety sold in a drugstore and used in the home is a water solution containing about 3% hydrogen peroxide. As you probably know, it is used as an antiseptic for small cuts and scratches. It checks the growth of bacteria. Hydrogen peroxide is composed of the same elements as water, namely oxygen and hydrogen, but in different proportion. Hydrogen and oxygen combine to form two different compounds. Water contains 1 part hydrogen and 8 parts of oxygen by weight, while hydrogen peroxide contains 1 part of hydrogen and 16 parts of oxygen by weight. There is twice as much oxygen in hydrogen peroxide as there is in water. Hydrogen peroxide is not a stable compound. This means that it does not remain hydrogen peroxide for long. It endeavors to get rid of the extra oxygen and break up into water and oxygen. The oxygen which it liberates is called nascent oxygen. It is highly active chemically and searching for something with which it can combine. If it meets bacteria, it destroys them. In this experiment, you can use the ordinary hydrogen peroxide found in the medicine cabinet. It must be fresh because, as already stated, it loses its oxygen and the liquid in the bottle becomes water in time. You may wonder where to obtain some magnesium dioxide. That is easy. Cut open an old dry cell, either a flashlight cell or a number 6 cell. The black powder inside is a mixture of manganese dioxide and carbon. You can use a mixture in place of pure manganese dioxide in this experiment. Put enough hydrogen peroxide in a test tube to fill it to the depth of about 1 inch. Then add a pinch of the mixture of manganese dioxide and carbon. The liquid in the tube will bubble and fizz. The manganese dioxide causes the hydrogen peroxide to break up rapidly into water and oxygen. The bubbles in the tube are bubbles of oxygen. Light a broom straw and blow out the flame so that only a red-hot ember remains at the end. Thrust this into the test tube. It will glow brightly and burst into flame. Like all other flames, the flame of a candle is burning gas. It is gas which is uniting with oxygen so rapidly that it gives forth light and heat. Modern candles are made of a mixture of the waxy hydrocarbons, stearin and paraffin. When a candle wick is lighted, the stearin and paraffin melt and soak into the wick. The heat of the burning wick changes the melted waxes into gases which burn. In these gases are the elements of which stearin and paraffin are composed. Herein lies the answer to the question, where does a burning candle go? The solid matter of the candle melts and is decomposed into hydrogen and carbon by the heat of the flame. The hydrogen burns immediately, forming water vapor. The carbon is first heated by the flame until it becomes red hot. Then it burns, forming carbon dioxide. It is the burning carbon which produces the familiar yellow color, characteristic of a candle flame. Some of the carbon escapes without burning, and you see it leaving in the form of smoke. A candle is a miniature gas factory. When a candle is lighted, it generates gas until the wick and wax are entirely consumed. If the candle flame is extinguished, the wick and wax cool sufficiently so that after a few seconds, gas is no longer produced. We can perform an experiment where there is no strong air draft. We can light the candle, and when it has burned for several minutes, light a match and blow out the candle flame. Immediately hold the lighted match about 3/4 of an inch above the wick and in the smoke which arises from the wick. The smoke is actually gas. It will ignite, and the flame will move downward to the wick and relight it. If you wait too long after blowing out the flame before holding the match above the wick and wax will become so cool that the experiment will not work. The gas in a candle flame. We can capture some of the gas in a candle flame. There is unburned or only partially burned gas close to the wick. We can light the candle, and when it is burning well, hold one end of a glass or metal tube about 6 inches long and the flame directly over and close to the wick. The tube may be either of glass or metal with an inside diameter of about 1/8 inch. A piece of soft seamless copper tubing of the variety used for oil or gasoline lines will serve. Hold the tube in a slanting position so that the end not in the flame is slightly higher than the other end. When the correct position is found, smoke will issue from the tube. This smoke is the unburned gas or vapors of hot stearin and paraffin. Hold a lighted match to the end of the tube and the gas will burn. There is carbon in a candle flame. You will have visible proof of this statement if you perform the next experiment. It will probably be a surprise to find that such a black, sooty element as carbon exists in the white wax and brilliant flame of a candle. For that matter, you could, if you knew how, also find carbon in other seemingly unexpected places, such as in soda water and chalk and in your breath. The carbon in a candle flame can be detected by chilling it below the temperature that is necessary in order for it to burn. Light the candle, and when it has been burning for a few minutes, hold the bowl of a cold spoon in the upper part of the flame for a second. A piece of cold glass or the edge of a white china saucer can also be used as well as a spoon. Whichever is used, it must be withdrawn before it has an opportunity to become hot. You will find it to be covered with a deposit of fine powdery black carbon called lamp black. Large quantities of lamp black for use in the manufacture of automobile tires, concrete, and paints are produced in much the same manner, but not with candle flames. Flames of natural gas from gas wells are used, and the lamp black is deposited on steel plates kept cool by water circulating over them. Whenever a hydrocarbon is burned, water is one of the products. The large amount of water produced by internal combustion engines which burn hydrocarbons in the form of gasoline or diesel oil has already been mentioned. Carbon dioxide also is produced when a hydrocarbon is burned. It is estimated that about 90 cubic feet of carbon dioxide pour out of an automobile exhaust pipe for every gallon of gasoline burned in the engine. Since stearin and wax contain hydrogen, water is produced when they burn. The best tasting steaks and chops are those that have been broiled over a charcoal fire. Cooking outdoors over a charcoal fire is a popular holiday pastime, but it is not a new idea. Because wood charcoal burns with no smoke and practically no flame, it has been used as a fuel for thousands of years. The occupation of making charcoal, called charcoal burning, is one of the oldest trades and incidentally has been always one of the most poorly paid. For many centuries, until a few decades ago, the method of making charcoal remained unchanged. It consisted of heating wood without access to air so that it charred but it did not burn. Wood was piled up and covered with earth and sod, and the wood at the bottom of the pile was set on fire. Small openings only were left in the sod and dirt through which a limited amount of air could enter and smoke could escape. Because the supply of air was restricted, the wood could not blaze. That at the bottom of the pile smoldered slowly, while that in the upper portion could not burn at all for lack of oxygen, but was heated and charred by the wood below. To some extent, the chemical action which took place in the charcoal making resembled the natural process by which coal was formed. Wood and other vegetal matter are composed largely of hydrogen, oxygen, nitrogen, and carbon. When wood was charred into charcoal, the hydrogen, oxygen, nitrogen, and some of the carbon escaped in the form of gas and smoke. Charcoal consists principally of carbon. So does coal. That neither is pure carbon is shown by the fact that they leave an ash when burned. Pure carbon leaves no ash. The process of making wood charcoal is the chemical process known as destructive distillation. The old-time charcoal burner was unaware that in the smoke and gases escaping from his heap of sod and wood were substances more useful and valuable than charcoal he manufactured. When chemists discovered the nature of these gases, a new industry was created, and today wood is turned into charcoal, not only to obtain charcoal but also to secure certain byproducts. A byproduct is something produced in addition to the main product in manufacturing. The byproduct in charcoal burning are pyroligneous acid, creosote, and wood tar. The wood which is to be turned into charcoal is enclosed in a steel oven called a retort and heated with natural gas or oil. The gases and vapors from the wood pass out through flues and are cooled and stored. A cord of seasoned hardwood yields about 1,000 pounds of charcoal and 7,000 to 9,000 cubic feet of gas. Scrap wood and sawdust, materials which ordinarily would be waste, can be used in the retort. alcohol and vinegar made from wood. The pyroligneous acid in the gas from the charring wood is refined and produces menthol alcohol or menthol, used as antifreeze in automobile radiators. Acetone, acetic acid, and a number of other things. The destructive distillation of wood is an important industry in Pennsylvania, New York, Michigan, and Tennessee. Beech, maple, oak, and hickory are the principal woods used. Some of the things that are needed for an experiment with the destructive distillation of wood would be a 1/4 pint compression lid can, sawdust, 10-penny common nail, matches, and a stove. What we do is to punch a clean round hole through the center of the lid with a 10-penny common nail. This size of nail is 3 inches long and will make a hole of the right diameter. If the hole is too small, the gas generated in the can will escape with too much force. Fill the can with sawdust. White pine, oak, beech, maple, or hickory sawdust will be most satisfactory. The sawdust from yellow pine contains too much rosin for this experiment. Press the lid tightly in place and set the can over a lighted burner on a gas stove. When white smoke pours out through the hole in the can lid, light the smoke with a match. It will burn with a yellow flame like illuminating gas. It is gas and water vapor. After a few minutes, the water vapor ceases and gas alone comes forth. The gas continues to burn. It contains tar and pyroligneous acid. By proper chemical treatment, it could be changed into such substances as creosote, menthol, and acetic acid. It will be necessary to regulate the gas burner so that the right amount of heat is supplied. If the fire under the can is too hot, the gas will be forced out of the hole in the lid in such great volume that the flame will be blown out. When no more gas issues from the can, turn out the fire and let the can cool so that you can open it. You will find that it contains powdered charcoal. The Ford Motor Company turns out all of its scrap lumber from old packing cases, etc., into charcoal. The gases are collected and used for making lacquer for automobile bodies. Powdered charcoal from the retorts is pressed into large pellets called briquettes. These are ideal fuel for a barbecue. There are two divisions of chemistry. Compounds are divided into two main groups called organic and inorganic. Organic compounds are the compounds of carbon. Inorganic compounds do not contain carbon. The student of chemistry is taught the principles of inorganic chemistry first. The term organic came into use long ago. At that time, there was a mistaken notion that the carbon compounds found in plants and animals could be made only with the aid of the mysterious life force that exists in living plant and animal organisms, but not in minerals. This mistaken belief was shattered in 1828 when a German chemist named Waller succeeded in making urea from inorganic substances. Urea is an important organic substance or compound. Since that day, there has been no limit to the number of organic compounds which chemists have been able to imitate or create. Estimates place the number of organic compounds now known at more than 500,000, whereas all known compounds of all the elements other than carbon total up to only 26,000. Organic chemistry is closest to our immediate personal interests. The chemistry of our bodies is largely but not wholly the chemistry of organic compounds. So also is that of thousands of things about us, such as our food, clothing, furniture, paper, medicine, dyes, rubber, perfumes, soaps, etc. Practically all organic compounds are grouped in the following classes: 1. Hydrocarbons, 2. Alcohols, 3. Aldehydes, 4. Acids, 5. Esters, and 6. Carbohydrates. At present we are interested in hydrocarbons. A hydrocarbon is a compound containing only hydrogen and carbon. Acetylene, benzene, turpentine, naphthalene are important hydrocarbons. Hydrocarbons also occur extensively in petroleum and fuel gas. Hydrocarbons are to the chemist what lumber is to the carpenter. He can make many things out of them. Coal is one of our best sources of hydrocarbons. There are two varieties of coal. There are very few industrial processes which do not require fuel and power. Electricity generated in hydroelectric plants and petroleum products supply some of our heat and power needs, but coal is the principal source. There are two kinds of coal: anthracite or hard coal and bituminous or soft coal. Soft coal is the most important fuel. It is more plentiful, cheaper, and produces a longer flame than hard coal. It is the coal most widely used in power plants. There are many grades of soft coal, and although the chief use of them is as fuel, certain grades are used for making coke. If the right kind of soft coal is put in a closed oven and heated in the absence of air in the same way that wood is heated to produce charcoal, the result is coke. Nearly 40 million tons of this special fuel are produced every year in the USA. Coke is used principally in blast furnaces to smelt iron from its ores. The treasure in a pile of coal. Not many years ago, coke was produced solely to obtain coke, just as charcoal was produced to obtain charcoal. The gases and vapors which were produced were wasted by being allowed to escape in the air. The neighborhood in the vicinity of coke ovens reeked with nasty odors. Then for a time the gases from some coke plants were stored in huge tanks and sold as illuminating gas. In order to make the gas fit for this purpose, it was washed and purified. In this process, some ammonia and tar were recovered and they could be sold. In general, however, nothing was produced in a coke oven but coke and a sticky, smelly tar, which is somewhat of a nuisance. At least it was until chemists did something about it. Chemists have great curiosity and are always looking for something they can use which can be secured free or at low cost. In the vapors and tars of the coke oven they found chemical treasure chests. In these evil-smelling substances were benzene, toluene, xylene, phenol, naphthalene, cresols, anthracene, phenocene, and carbazole. Most of these names mean nothing to you, but they are raw materials from which a host of things can be made. They are a good illustration of the magic which is chemistry, because from them a chemist can make thousands of brilliant dyes, pain-killing and disease-healing medicines, fertilizers, explosives, food, preservatives, plastics, disinfectants, antiseptics, perfumes, roofing compounds, photographic chemicals, paving compounds, wood preservatives, flavors, and even rayon stockings and bristles for brushes. This experiment is quite similar to one described previously. However, bituminous coal is used instead of sawdust. This kind of coal is not difficult to obtain in some regions where it is the only variety available. In the northeastern part of the United States, where anthracite coal is used, it may be necessary to obtain a lump of soft coal at a coal yard or a power station, or look for a piece along railroad tracks. A small compression lid can with a hole in the lid as described before is required. You can use the same can if you clean out the charcoal. Here we would crush the coal into a fine powder and put 3 or 4 heaping teaspoonfuls in the can. Press the lid tightly in place and set the can over a lighted burner on a gas stove. When smoke comes out of the hole in the lid, it is a signal that gas is being generated. Because it has a bad odor, light it. It will burn with an odorless, smoky yellow flame. The burning gas and vapor contains its substances as tars, pitches, benzol, toluene, oxole, solvent, naphtha, ammonia, sulfate, sulfur, phenols, cresol, and naphthalene. When no more gas issues from the cap or can, turn out the stove and let the can cool so that you can open it. The gray material remaining in the can is coke. Today, nothing in a modern coke plant is wasted, not even much of the smell. 1 ton of bituminous coal carbonized in a modern Koppers coke plant yields the following products: coke and coke breeze, gas for heat and power, coal tar, light oil, miscellaneous chemicals such as ammonia sulfate, benzol, and others that we have already mentioned. This next part pertains to fuels for the human engine, a medicine which is found in seawater, and the experiments with cow's milk. Apart from certain minerals and the compounds known as vitamins, there are 3 classes of food essential to the well-being of mankind. These are proteins, fats, and carbohydrates. Starch is one of the group of chemicals which chemists and dietitians call carbohydrates. Sugars are also carbohydrates and are so closely related to starch that they might be termed first cousins. Starch is not merely a substance which is used in laundries for stiffening clothes. Since it is a carbohydrate, it is one of our most important foods. Starch, sugar, and fats are to human beings what gasoline is to an automobile engine. They are fuels which we burn to obtain energy. Cereals, vegetables, and fruits are our sources of starch. We get most of it from cereals. Wheat flour and consequently foods made of it contain much starch. So do potatoes, barley, rice, and tapioca. Starch is used in several manufacturing processes. It is extracted from wheat, potatoes, and corn and used in coating paper and in making alcohol, dextrin, and glucose. The adhesive on the back of postage stamps and the flaps of envelopes is made from dextrin derived from starch. Starch can be found in any kitchen where there is a good stock of food. It is not possible to tell whether or not a substance is starch or contains starch by merely looking at it. Fortunately, starch can be identified quickly by a simple chemical test. Iodine can be used to detect starch. When starch and iodine meet, they produce a deep blue color. This makes an interesting experiment. Before we do this, let us discuss iodine. What is iodine? Probably you have had a small cut or scratch treated with a dark brown liquid called iodine. Its full name is tincture of iodine, and it is often found in the household medicine chest. Tincture of iodine is made by dissolving iodine crystals in a small amount of potassium iodide or sodium iodide in alcohol. Iodine is one of the elements. Potassium iodide and sodium iodide are compounds composed of potassium and iodide and sodium and iodine. They are included in tincture of iodine to make the iodine mix with water and to preserve the strength of the tincture. When fresh and pure iodine forms steel gray crystals, these turn quickly to purplish black when exposed to air. The iodine needed to make medicines and the iodine compounds used by chemists and photographers is obtained in the USA from sea water, salt wells, and Chile saltpeter. In Japan and some European countries, it is secured from the ashes of seaweed. Tincture of iodine kills many varieties of bacteria and is used to disinfect wounds, but it is also irritating to the tissues, and consequently its value for wound disinfection is in dispute among medical authorities. If the tincture is too strong, the tissue injury it produces may more than offset its antiseptic value. On the other hand, some of the substances used as substitutes for iodine have very little ability to kill germs. A bottle of tincture of iodine should be kept corked tightly so that its alcoholic content cannot evaporate and make the solution stronger. We would all be pitiable without iodine. A small amount of iodine is necessary to the good health of human beings. Lack of this essential element causes sensitiveness to infection, lowered mental and physical activity, nervous disturbance, overweight, deformed bodies, goiter, and idiocy. There is enough iodine to supply human needs in cod liver oil, iodized salt, seafoods, fish, vegetables, cereals, dairy products, and fruits, provided the vegetables, cereals, dairy products, and fruits were produced on soils containing sufficient iodine. There are areas in the USA where little or no iodine exists in the soil. These are called goiter belts. Vegetables and fruit grown in these areas do not contain sufficient iodine to provide good health.